Good evening, everyone. Welcome to Lecture 25 of Kinematics and Dynamics of Machines. Tonight we will be covering bevel gears. In our previous lecture we covered worm gears and helical gears, so tonight we're going to finish Chapter 7. We'll also touch on Chapter 8, which will be the last new material that we're covering in this course. By the end of tonight, you should be able to accomplish homework problems 7.24 and 7.25. So please do give those a try and test your skills. So bevel gears. We've already covered spur gears in Chapter 6. Chapter 7 we've already looked at helical gears and worm gears. Bevel gears are a little bit of a different animal. They're fairly easy to understand. Here you see a very large bevel gear set, as judging by the feet not too far from it. Those aren't my feet, by the way. Bevel gears are used to transmit power between shafts, that intersect at some angle. We most often see bevel gears on shafts that are intersecting at 90 degrees, but other angles are certainly possible. The gear form of a bevel gear is actually a set of rolling pitch cones, so it's somewhat different from the helical gears that we previously looked at, which were really a set of rolling pitch cylinders. So for the next little bit, we're going to be looking at this picture, and I'm going to be pointing out some of the bevel gear terminology. The terminology is a little bit different than what we've looked at previously with both spurs and helical gears. So please take the time to pause this or to look very closely at this figure as we go through. So as I said, bevel gears are based on rolling pitch cones. The pitch cone can be seen along this line on both sides. That's the pitch cone that this bevel gear is based upon. It runs through the pitch surface on the face of the teeth and then comes up to this meeting point, the apex of the pitch cone. That's the intersection of the elements that make up this pitch cone. There's some other things that we need to know about this. One is the cone distance. So the cone distance is the slant height of the pitch cone from this apex out to the furthest point on the gear tooth. There are two additional cones that we look at here. The face cone is the cone that runs through the tip of these teeth. So it generates the outer cone of this bevel gear. The root cone runs through the bottom of the teeth. In addition to those two things, we have a couple of related things. The face angle, that's the angle that the face cone makes with the axis of rotation of the gear. There is correspondingly a root angle, which is the angle that the face of the root cone makes, and a pitch angle. And that, of course, then is the angle of the pitch cone to the axis of rotation of the gear. Just like with cylindrical helical gears, there is a face width for bevel gears, and just as with spur gears and all the other gears we've looked at, there is an addendum. That's the portion of the tooth above the pitch line, and a dedendum, the portion of the tooth below the pitch line. The addendum and the dedendum separately have, and they're shown over here, an addendum angle. So the addendum angle is the angle between the face cone and the pitch cone. The dedendum angle is the angle between the root cone and the pitch cone. The inside pitch diameter, that's the end of the teeth here. The diameter based on the axis of rotation of the gear at the intersection of the end of the teeth with the pitch cone. The outside pitch diameter is similar. It's just the outside of that pitch diameter. Then finally, there is a back cone. The back cone is formed by the elements of this tooth perpendicular to the pitch cone elements. So this is the back cone. And there's a back cone radius. And that back cone radius is from the pitch cone where it intersects the end of the tooth out to the intersection of the back cone with the axis of rotation of the gear. Normally what you will find is that the face width of bevel gears is restricted. They try and keep that down to no more than about a third of the cone distance, because as you can imagine, if you've got all of this contact and you've got a couple of bevel gears with their big beefy teeth pushing against one another, there can be a lot of force and a lot of deflection. So to try and manage that deflection, you try to keep the contact down a little bit, try not to take quite so much load. Now, bevel gear teeth are an interesting thing here. Bevel gear teeth are actually involute teeth. They don't necessarily look like it, but they are. The shape of the involute is scaled across the tooth face from a maximum size at the outer edge. Go back and look at this. Here's the outer edge. So this is the maximum size of an involute tooth profile, and it scales down to its minimum size at the innermost portion of the tooth. Obviously, if you continue that scaling all the way out to that theoretical apex point here, the tooth will get infinitesimal in cross-section. This is called the Treadgold tooth shape approximation, and believe it or not, these tooth shapes are actually based on the same shape that we use to generate an involute curve for a spur gear. You can find additional information on this online. There's really not much in your book, but you can take a look at the cross-section of the largest part of the tooth as being identical to the cross-section of an involute spur gear, where the pitch diameter is 2 times the back radius. So again, if I go back and take a look at this, here is my back cone radius, and what we would say is that the pitch diameter is 2 times that for the size of tooth that would be on a bevel gear. You can also look at it as having an imaginary number of teeth based on this equation. Now, there are several classifications of bevel gear, normally done by pitch angle. In most of Europe, specifically the UK, where we can communicate directly with what at least passes for the same language, a gear with a 90-degree pitch angle is called a crown gear. So actually, if you are talking to someone in the UK or oftentimes in the rest of Europe, you will find that what we call a ring gear in an axle or other large gearbox, they would call a crown gear. This angle can change. Generally, for the kinds of bevel gears that you find, that angle is less than 90 degrees. So you get an angle like this, a pitch cone that is positive. You can actually have that angle be greater than 90 degrees, so the teeth then would be aimed in, and the apex of the pitch cone would be beneath the gear instead of above it. That's generally not done because that kind of gear is very, very difficult to cut. But obviously, as additive manufacturing becomes more common, that becomes easier and easier to deal with. The velocity ratio of bevel gears is the same as the velocity ratio of any gears that we've looked at. So, the radius of gear 1 divided by the radius of gear 2, the number of teeth for gear 1 divided by the number of teeth for gear 2, or if we're looking at speeds, the speed of gear 2 divided by the speed of gear 1. When you're looking at the radius for bevel gears, that radius is the pitch circle radius. Another parameter that is very important for bevel gears is the pitch angle. When we look at a set of bevel gears, what we find is that the total pitch angle or shaft angle is equal to the pitch angle of one of the gears plus the pitch angle of another. You can see that here schematically. The dashed center lines are the axis of rotation for the gears. The total angle between those axes of rotations or shafts is sigma. And then positive and negative gamma are the pitch angles of the gear and the pinion, respectively. There's a relationship between bevel gear teeth and angles. As you can imagine, there's gear relationships for almost everything. So, if we have our velocity ratio, in this case represented by the pitch radius of the pinion divided by the pitch radius of the gear, that's also equal to the number of pinion teeth divided by the number of gear teeth. We can relate the angle, the bevel gear tooth angle for the gear as being equal to the sine of the shaft angle divided by the velocity ratio plus the cosine of the shaft angle. For the pinion, the tangent of gamma is equal to the sine of, again, the shaft angle divided by the reciprocal of the velocity ratio plus the cosine of the shaft angle. When the shaft angles are at 90 degrees, these two relationships simplify to be very, very easy. So, with that in mind, let's take a look at sample problem 7.7. This is on page 501 in your book, and it's fairly straightforward. We have a pair of straight-toothed bevel gears, and it's mounted on shafts that intersect each other at an angle of 70 degrees. So this whole angle between the shafts is 70 degrees. The velocity ratio between these two gears is 1/2, and we're asked to determine the pitch angles of the gears. So, we know obviously the shaft angle, sigma, 70 degrees, and we're given the velocity ratio as 1/2. This is actually just engineering student heaven, plug and chug. We have this relationship that was previously given for the tangent of the pitch angle or the cone angle for the gear. If we plug in our shaft angle of 70 degrees and our velocity ratio, we actually find that that angle is 48.2. Same thing for the pinion gear. We get an angle of 21.8. And as a double check, if we add these two together, that would be 70 degrees, which is our shaft angle. It checks. Now, forces in bevel gears can be pretty extreme. In particular, the most common bevel gear application that I'm familiar with is an automotive differential. And if you have seen a differential, I would normally show you a picture, but you can do a search on your own for it. A differential is a fairly heavily built gearbox. We can assume for these bevel gears that the tooth load acts at the center of the tooth, so the mean pitch radius. Therefore, if I add the inner and outer pitch radii and divide by 4, that would give me my mean pitch radius. Here's a schematic from your book, it's figure 7.22, showing bevel gear forces. We have a normal force that's acting on the tooth, and that's going to resolve then to two other forces. This is a little bit different than what we're familiar with from spur gears, helical gears, and worm gears. So, for a given pressure angle, because remember that our shape of the tooth is still an involute curve, we can calculate the tangential force on the pinion gear as being equal to the normal force multiplied by the cosine of the pressure angle. The radial force for the pinion then can also be resolved based upon both the pressure angle and the pitch angle for the gear. But there's not only a radial force here, and a tangential force, there's an axial force. So these gears are still trying to force each other out of mesh, and you have two forces to contend with as they try and push each other out of mesh. The radial force and the axial force. Concurrently, the forces on the mating gear can be found with these equations. For shafts that are 90 degrees apart, it's worth noting that the axial force on the pinion is equal to the radial force on the gear, and the radial force on the pinion is equal to the axial force on the gear. But the tangential forces for both, again, are the same, both for the pinion and the gear. They will have the same tangential forces, and therefore we can calculate the torque being generated upon each of those gears, or around each of those gear shafts. So, that's bevel gears. Bevel gears are fairly simple, fairly easy to comprehend. We really only have one additional thing to look at that we'll be working on as far as new material for this term, and that is gear trains. So I just want to introduce that a little bit, and then we will carry on with it in the next lecture. So gear trains. As you're probably aware, most of the things that we have that produce rotary power do so at a fairly high speed. An internal combustion engine that's loafing along at 1,000 RPM is still turning at a fairly high speed and really does not make a tremendous amount of power until that speed goes up. An electric motor can be stationary and providing a significant amount of torque, but it's not putting out power, because as you remember, power is equal to torque times speed. So, gear trains are used in our technology in order to take that fairly high-speed rotary power and step it down to a speed that's useful for the kinds of things we're doing. Gear trains can be used for things as disparate as automotive transmission, where we're taking the output from a 3, 4, 5, 6, if you're crazy, 7, 8,000 RPM engine and stepping it down to a wheel speed, or for precisely timed motions, things like clocks, or to change the direction of rotation for an output power. Quite a variety of things. As an aside, and here is an extra credit opportunity for you, I will post this on Blackboard as well as an announcement. If you would, please take a look at the name John Harrison, Harrison. He lived from 1693 to 1776. John Harrison was instrumental in the design of a very, very important gear train. So what I would like you to do is find out a little bit more about John Harrison, what gear train he designed, at least one other ancillary technology that came out of his work, and write up, say, maybe a page. It can be double-spaced, don't fret about it too much, but a page about John Harrison, why he did what he did, what the outcome was, and what, if any, additional technologies you were able to find that came about as a result of his work. So, anyways, here we have a couple of gear trains. This particular one probably looks fairly intriguing. It's got a worm gear, or excuse me, a worm that's rotating a worm gear. That worm gear then is directly rotating a secondary gear, so a fairly high gear reduction. Over here we have a very complex kind of gear train. This particular one is coming out of a clock or a watch, but they're both gear trains. When we look at gear trains, and hearkening all the way back to the fundamental law of gearing, we're looking at something that is generating a velocity ratio between an input speed and an output speed. But now we're going to start treating that velocity ratio just a little bit differently. Before, other than taking note of which direction things were turning, we really didn't pay a whole lot of attention to it. Now, though, we're going to start to pay attention to it, because as we mesh gears together, we are changing the direction of rotation. So we're going to start noting that by putting in negative signs. So we are going to change that direction of rotation every time we add a gear. So, also we want to remember the concept of idlers as we talk about gear trains. These, again, are oftentimes put in place for multiple reasons. In this particular case, for instance, we might put an idler in place so that our input gear and output gear are turning in the same direction. We might put an idler in place because we need to move from a shaft at the center of our input gear a little further than we otherwise would in order to get to where we want our output. We may even use multiple idlers so that we can maintain that change in direction of rotation. These are all concepts that are going to be important for us as we look at gear trains. So I will leave you with that. I know this is a little short, but I like to keep the lectures shorter towards the end of the year. We do have a couple of references you can take a look at. There's some additional information on Bevel Gears, very readily available on Wikipedia, also on gear trains, and there's a nice article in How Stuff Works on gear ratios. So hopefully at this point you've had enough of gears for one evening. I will see you then at the next lecture, and we will continue on with gear trains.